All right. Welcome, everyone, to the second presentation of the MSU Science Festival digital live session. And we are going live now with Umakanth. And he is, sorry, I just lost my feed here. He is the owner of an IT company called Symbiosis International based in Okemos, Michigan, where he lives with his wife. He has 2 master's degrees in computer science. He is a top 10 innovator in the nation and a Michigan 50 company. And he's going to talk to us a little bit about his STEM for All activity, which he's doing to get kids interested in building science exhibits. And then he's going to give a live demonstration. So I'm going to turn it over to Uma, and he is going to give us a list of things that you can get from your home to do the demonstration live while he's doing it. So take it away, Uma.
Good morning, everyone. My name is Uma, as Roxanne mentioned. I am the founder of STEM for All. It is an organization dedicated to spreading STEM education for people of all socioeconomic backgrounds. And today I'm going to be showing a few things about gravity, the invisible force, and explained by Newton in one way and Einstein in a different way. For the demonstration, what you need is, the list is a few coins, paper clips, 2 paper clips, a string about 2 feet. That's all you need. And one of the STEM for All students, a future scientist named Christina Susan Joseph, has made a video of how to make this, and I will be showing that video later. She is a middle school student in Okemos, and she has been with STEM for All for a while, and learning and educating me too. At STEM for All, we want to create an entire science center, low cost, built entirely or mostly by school students. And in this science center, you can actually see an exhibit, touch it, play with it, experiment with it, break it accidentally and probably even intentionally, repair it, rebuild it, improvise it, and make a copy and take it home. That's the kind of science center that I want to be building. And I want to keep it in every public library, every school, every village in every country. And I need help from students like you, high school students and all the way to the newborn babies. So I'm going to, as I mentioned, today I'm going to be talking about gravity, explained by Newton in one way, and I'm going to show some of the things. Bear with me, I'm going to change the screen, camera to a different mode. Newton, when Newton was, are you able to show all these things? When Newton was telling about, researching about the gravity, he came up with one thing, that if there is an object, if there is something mass that is not acted upon by any force, it is going to remain at the same place, or if it is moving in it's going to move in a straight line. This particular surface is not very horizontal, and so it is moving away. And Einstein said that if there is mass, it bends the space-time. So from Newton's point of view, if there is something, it doesn't bend space-time or anything. That kind of concept itself was not there during Newton's time, space-time as an entity at all. So when Einstein came with that one, he said that when there is a mass, it bends the space-time. So this is a small mass, it bends a little bit. This is something much heavier, it bends it much more. So you can have something like Newton's law of gravitation. If there are two masses, they attract each other depending upon and proportional to the mass of each objects. If they are closer, they attract more. If they are farther, they attract less. And I'm going to show that kind of thing here. If I'm going to keep this just only one, it is bending the space-time a little bit. I'm going to keep them away and see what happens. Well, because of the type of stretching fabric, they're supposed to be actually coming towards each other and then hitting each other. That's what it is. So this particular thing is actually made of stretchy material, lycra, spandex. Those are some brand names, and this is actually given by my classmate Subramaniam. Thank you very much. And I'm going to show a few things that Newton came up with that we can demonstrate using this. Assume this is a mass that has bent the space-time and call it Earth. If there is something here, it is going faster, like it is being pulled faster. If it is far away, it starts slower and then moving faster here. Very similar to what I throw. So Newton was able to conceive that objects attract each other. And for example, the Earth here, if this is the moon, it is attracting the moon. And if the moon is moving this way, it is constantly being pulled. And so it goes in a circular path. And Newton was able to tell about if we are in a mountain, for example, this is the mountain, and then we fire a cannon. The cannonball will come and hit the Earth. And if you fire it faster, it goes further. At a sufficient speed, it starts going around the Earth. It can go in a full circle, and if there is no resistance, it can go around the Earth forever. And he said that is how moon is going around the Earth. He was able to get this one 300 years back. So here again, without this mass, this is supposed to be going in a straight line. Okay. I'm going to demonstrate something called the escape velocity. This Earth is giving a gravity well, and if you are actually throwing, say for example, a ball is being thrown like this, farther and farther, but if I am able to throw this sufficiently faster, and assuming there is no ceiling and there is no atmosphere, it will go out of the Earth's pull and go forever, and that is the escape velocity. In this case, let's assume that this is the infinity. Now, if you throw it if you throw this one fast enough, it goes away. The same way it can also be done in the any other direction also. It goes away. Now, this same thing can be used to demonstrate how Chandrayaan and Beresheet rockets, spacecraft, went from Earth to the moon. So what they did was have the spacecraft have the engines, but they were in the low Earth orbit. So they were going like this, but they made it into an elliptical orbit like this, and then each time it comes to the closest position of the Earth, they'll give a boost to this one. So it goes around like this, again goes like this. It kept on increasing the elliptical path until at some point it reached the gravitational field of the moon. So that is what I'm going to demonstrate now. Now, this becomes the Earth, and this is the Moon. And I'm going to demonstrate something called a free return. And it's not working, but it will. That's what it is. The free return is when the spacecraft goes closer to the moon, pulled by the moon, and comes back on its own to the Earth. I'm going to try a few more times. It was all working very well yesterday. Yeah, that's what it is. See? That's what it is. Yeah. And in fact, there is a path that where it can go around the Earth and the Moon forever. Okay, you can put it on the other board. Camera, you can switch it on to the. Okay, I'm going to ask you for any questions. I'm back here and see if there is any questions. Roxanne, is there any question?
Right now, we don't have any questions, but you were talking about mass bending space. What would be an example of mass that's bending space?
Well, any mass is, per Einstein, any mass bends the space-time, curve space-time. So Earth, for example, Earth is a huge one, and it has it bends the space-time in such a way that we can call it a gravity well. So in that well, things are being attracted by the Earth. If they are closer, then they are attracted more, and if they are farther, they are attracted less. And the inverse square law works on this. Whereas in the demonstration I gave, it depends upon how the fabric stretches. The fabric, if it is stretching uniformly, that's the free return, that trajectory that I mentioned, that should be working very good. And this is a very small model, so it was not working perfectly. But this is something that we wanted to have it at the planetarium, where the kids can just try many times, and if they are trying, say, 10 times, maybe 4 or 5 times, it will be working.
Okay, and we do have a question from Lori Ann. She wants to know how and why does it curve?
Well, I have to ask Einstein.
Ah.
He mentioned this model is something, just a model. It is to visualize how mass bends space-time. But it is quite a complex one. And if this is being done by the STEM for All students, they will be saying, wait till I get my PhD.
Okay. So another question was, how does gravity work?
How does gravity work? Yeah, gravity is again the per Einstein, it is the bending of space-time, the curve that is produced by the mass on the space-time. That is what is called gravity.
Okay, so if we jump up, we're not just going to jump up and never come back down to Earth because we are being pulled down by the Earth's gravitational force.
That is correct. Yeah, we don't have enough power to actually jump all the way. That is faster than the escape velocity. And again, we are going to assume that there is no atmosphere that can burn if you are going that fast.
So if we were on a different planet, Could we jump further or?
Yeah, for example, if we are on the moon has on the surface, it has about 1/6 the gravitational pull compared to the Earth. So we should be able to jump much higher. And if we are on, say, Jupiter, and assuming it has a surface, it doesn't. So somewhere from there, it doesn't have a solid surface. It has a surface, but so assuming that we are jumping from Jupiter, we won't be able to jump. Probably we will be crushed by its gravity.
By its gravity. Okay. And Kayla just had that same type of question. Is the effect changed by the type of medium the mass is in, space versus on Earth?
The type of medium does not matter at all. In fact, that is something that gravity, its effect is all the way to infinity. But as the distance goes, increases, the pull reduces by the inverse square law. Like if the distance doubles, then the pull is actually 1/4. If it triples, then it is 1/9.
Okay.
The main point I want to show in this one is that people will be able to play with this if they are actually physically be in that place. And it is something that they can actually do at home also. Take a plate and then stretch a t-shirt that say any sweat wicking t-shirt will be able to act as this cloth, and put something, some coins or something that will bend it. I'm going to show.
Okay, we have a couple of other questions. Kenneth has a question, is gravity constant? Does our gravity change even though we can't notice it?
Well, again, gravitational constant is something that is a constant. That is different from the pull that we feel. So on the surface of the Earth, the pull we feel is about, that is measured in meters per second. That's acceleration due to gravity. And if you go to space, if you go farther and farther away, it reduces.
All right. And let's see, Amanda has a question, and I'm not sure if you know the answer, but we'll give it a go. How do you slow down light? Can you?
How do I slow down light?
Yes.
Okay. Light in vacuum, it has a constant speed, 300,000 kilometers per second, 186,000 miles per second. So it is slowed down, meaning if it is passing through water or glass, it is slowed down. And scientists have some other complex ways of reducing the speed even further in the labs.
All right. Rita has a question. Why does the moon have less gravity than Earth?
Okay. Again, it depends upon how much mass is there on the moon. Moon is much lighter than Earth. So it has less gravity. And we have gravity, like we are, say, 100 pounds or 200 pounds or whatever be our weight measured here on Earth. So we also have gravity. We pull things, but it is very, very minute.
Okay, and Nancy is asking, this all makes my mind boggle. I'm only a layperson. How do we know this continuum is real?
So it's like a philosophical question, right? So one thing is that if we make some equations and then measure if it is working, if we have a model and then see that we make a prediction, and if that prediction is correct, then as far as that much, it is real. We can say that that is real. And we make some assumption like gravity is something that can change with the color of the t-shirt that I am wearing, and try to make an experiment. And then if it is not wearing, then our hypothesis that the color of the t-shirt I am wearing changes gravity. That's not correct. So that's how scientists make a prediction. When they make a prediction and they are able to actually find that prediction is working, then their model is correct. If it is not working, then they have made some mistake in the model.
All right. We have another question by Kayla. Is there a way to show our gravity pull in things?
That our gravity pulls anything?
Yeah, so is there a way, I guess, to show how gravity pulls things?
Well, if we jump up, we are being pulled down. So that is something that we can try. We can jump many times and then we get exercise as well as proof that 100 times the earth pulled us back to the earth.
Okay.
I want to show one video. I can take more questions, but I want to show the video created by Christina, the future scientist.
Okay. We have about 7 minutes left. So
Okay.
just to give you an idea of our time.
1 minute video, but that's the one where we can show the same thing. We had one more exhibit. I think we won't have the time to show that one, but yeah, go to YouTube and if you go to the history. That one, the 2D space. Okay, I'm going to show. This is Christina.
So she's attaching pennies to paper clips, right?
Correct. Yeah, that is the mass now.
Okay.
And then stringing them in that string. She made this video herself.
Now, hold both ends of the string tightly. This represents a straight line or single dimension. If the mass bends the space-time, they are attracted towards each other like in space. Two planets attract to each other with the bend caused by gravity.
Yeah, this is the experiment that they can do at home. And this is a very simplified model. Yeah, this is a very simplified model. What I did with the cloth in a two-dimensional, this is using just a string and demonstrating. If we have the masses closer, then we will show that it is being attracted more easily. And if it is heavier, again, it is going to be bending the string better and it is going to attract closer.
Okay, we did have one more question come in. Is it possible that there would be so much gravity that light would bend around it because light is both a particle and a wave?
That is correct. That is what was predicted by Einstein and having been experimentally verified many, many times. When Einstein predicted that the space-time curves and so the light also will be bent by gravity, there was no way to verify that. And fortunately, at that time, there was an eclipse, a total solar eclipse. And scientists thought that if scientists figured out there is a star behind the sun and see if its position shifts because the light is coming around the sun. And they were able to figure that they were able to experimentally verify, and Einstein became very, very popular after that.
Awesome. And then one more question from Rita. She wants to know, how is light both a particle and a wave?
Yeah, that's very, very difficult for me to explain because I don't have a good understanding of that one. Well, you have to wait till I get my PhD.
Okay. We have a few more minutes. If anybody else has any other questions, Uma is here to answer those. And while we have a minute without any questions, I'll say the Digital Science Festival is going on until 4:30 today. We have presentations every half hour. So look at the schedule and see what else is coming up. We're excited to have our 10 presenters. And then we have things going on throughout the month of April as well. Since we're all staying home and staying safe, this is a good way to do some science in your own homes.
Yeah, I want to actually thank the MSU Science Festival for giving me this opportunity, and also all the students who have been working with the STEM for All to build the Science Center. And I want to thank the sponsors, Symbiosis International, the Community Foundation, Meyer Wakimas, James and Kimberly Curry Foundation, Rotary Club of Lansing Foundation, and MSU Federal Credit Union. And I don't want to forget to thank my wife for letting me use the living room for this, and my daughter helping me in every way. And I want to make sure that the school students, if they have the time to work with me online, I will be happy to help them, coach them, build exhibits.
Does STEM for All have a website they can go to?
Yes, it is STEM, STEM, number 4, ALL.net.
Awesome. And if you have any questions or want to look at the schedule of what's coming up, you can go to sciencefestival.msu.edu for future events. And with that, our time has come to a close. Uma will be online for a few minutes if anybody has any other questions. And thank you for viewing.
Thank you very much, everyone.